Okay, thank you very much for giving me the opportunity of presenting Capture Project and other developments that we are doing here at CENER. Okay, I will make a brief introduction about CENER, what we do. Then I will talk about the solar power tower potential and constraints. Then I will be focusing Capture Project, and finally I will mention other projects related to the solar towers that we are doing here at CENER. Okay. Then CENER is the Spanish National Center of Renewable Energies. We are working in 6 research areas: wind energy, photovoltaics, solar thermal energy and thermal energy storage, biomass, energy in buildings, and renewable energy integration. We work mainly in R&D development and technology transfer. We also make testing of components and certification, capacity building and training, and of course, technical assistance and feasibility studies. In the end, we try to make technology transfer to the industry. Okay. In my department, we are 25 people with different skills, and we try to have to all the multidisciplinary approach. We are working in the 5 continents with a lot of publications, patents, etc. Okay. Now, the main business lines that we are having in my department are the line 1 is source assessment and measurement. Line 2 is focusing design and development of new components. The line 3 is more focusing technical assistance and consultancy. The line 4 focusing the testing and characterization of components and systems, and the final line is focusing in the thermal storage system. Now, if we look at the solar power potential and constraints, if we look in the past, in the year 2003, several studies shows that the solar towers has the greatest potential in terms of cost reduction. This is due to the high concentration. With high concentration, we can have high temperature in an effective way that allowed us to have a greater efficiency in the cycle, and also to have a most cost-effective storage. In the year 2013, the forecast for this technology was to have, let's say, about 6 gigawatts installed by 2018, overtaking parabolic trough technology. But the truth is that today, the installed capacity is much less than expected. We are installing solar towers about 1 gigawatt, and this is due to the uncertainty that how the investors look at this technology, the reliability. Not all the plants have behaved in the same way, and also the durability and the actual efficiency. And this is linked to the high temperature and also how to deal with this. Okay, so our approach in CENER is to work in Capture and other projects, trying to overtake the barriers of this technology, to pave the way for these technologies. Okay. The Capture project is funded by the European Commission. It's called Competitive Solar Power Towers, and the main objectives are the following. One is to reduce, of course, the levelized cost of electricity, proposing an innovative concept of plant. That is what we call multi-tower decoupled solar combined cycle. I will explain this afterwards. In this project, we also try to look at the heliostat production by making the size of the heliostat smaller. When we started the project, at least in Europe, the trend was to make the heliostat bigger and bigger. And also we had developed a smart calibration system. In other objective of the project, of course, to validate and test the most critical components like the heliostat, the receiver, and the regenerator system in a relevant environment. Okay, of course, we are not alone in this project. We have many partners here. I think most of the partners are already in this workshop. Okay, what is the multi-tower decoupled solar combined cycle? What is this? Okay, in this approach, we have several fields with a small size that allow the higher efficiency in the solar field. They are feeding Brayton cycles. The Brayton cycles are very cost effective in the range from 5 megawatts till 10 megawatts. You can find a commercial Brighton cycles with a high efficiency. Okay, and then these different towers are feeding a common thermal storage system. Okay. And then this common thermal storage system will feed a Rankine cycle. As you know, the Rankine cycles, to be cost effective, they need to be large. Let's say from the range of 50 megawatts or more, 100 or 200 megawatts. So the idea is to get the benefits of all this combination and finally to reduce the cost. Okay. On the other hand, our approach for solarizing the gas turbine is different to the former approaches. And I think from my point of view that this is a clever approach. In the former approaches, we usually have a receiver that was pressurized. In this case, we have an open volumetric receiver that is easy to handle. And this open volumetric receiver, this open volumetric receiver, charge a regenerator, and then the regenerator is pressurized with the circuit of the gas turbine. In this way, we are operating. So the complexity that we had at the beginning in the solar receiver is moved from there to the regenerator system that is mainly controlled by switching valves at high temperature. What gives us a higher flexibility and a better control on the system, okay, and keep the receiver more simple and easy to operate. Okay. And now the key components in this project are, as I told you, the heliostat field, okay, the solar receiver and the regenerated system. And we are looking to have this combined cycle with a high efficiency and with the concept, the tower concept, with a thermal storage system. That with this will increase also the flexibility because we can operate some of the towers or the whole of them depending on the needs of the energy system. Okay? Now, if I focus the development done in this project regarding the solar field, in this project we have developed a small size heliostat. It's a heliostat of about 8 square meters. Is made with components of the shelf. In this case, we have used an electric motor from the wipers of the cars, with is a very low cost motor. We are using a cable transmission that is also very low cost, and the whole prototype is being focused in use mass production and lean manufacturing techniques to ensure high quality and low cost. The idea is to have a low cost heliostat, robust enough, and we have been concentrating in reducing the cost of the tracking system. As you probably know, is the part of the heliostat that costs more. And with this approach, we have significantly reduced the cost of the tracking system. Of course, we do not think that this kind of system is going to have a long-term, let's say, repeatability as high as the typical worm gear mechanism, but we have developed in parallel to this a new calibration system that we call a smart calibration system I'm going to present now. Okay, this system, short smart heliostat calibration system, has been developed together with Technica. And in this idea, what we have attached a camera to the heliostat, and by combining an artificial vision system and the kinematic model, we can really calculate the actual parameters of each heliostat. In this picture, you can see in green, or we place around the heliostat several targets. So we are not going to use the sun to calibrate the heliostat, but several targets with a position that we know in advance. In our case, we have been using infrared lights. We place in these pictures, I don't know if you can see it, okay, in red, you can see some numbers here in this picture, okay, and these are the lights placed in Plataforma Solar de Almería, and in green, they are the places calculated by our kinematic model. So we place the heliostat, we say at the heliostat, okay, we think you are in this position and with this axis orientation, and then the system calculate where in which pixel we should see the light targets, and iterates. So it iterates from this initial model to the intermediate model to the final model. Once we are in the final model, all our parameters are fully in agreement with the real and actual position and orientation of the axis of the heliostat. This system can be done every night, and with this system we will guarantee that the heliostats are fully calibrated. This system can be made in parallel because all the heliostats can work at the same time. Okay, here you can see the test made in Almeria with our heliostat, the solar power plant, and the different targets, and the results with this method is we got the results of the movement prediction of 0.2 milliradians. And this is, in this video, you can see the results after calibrating the heliostat and aiming to the tower. So the results are very promising. We are using low-cost cameras, so it's easy to implement. And we think that with this system, we can use very cheap heliostat, or the system can be also used for other heliostats to be calibrated. Okay, in case you have an earthquake or other kind of things, you can calibrate the field very easily. Okay, regarding other developments within Capture, we have developed a solar receiver. This is an open volumetric receiver, similar to other present today. In this case, we have even used a ceramic foam structure. This foam is heated up by the sun, and then the air is heated up by passing through this foam, and this heat is finally charging the regenerative system. Okay, I'm going to show you this is the detail of the foam, and in the next slide you will see how this system is built and installed at Plataforma Solar de Almería. The other interesting system, as I told you, is the regenerative system. This system is controlled by valves that are charging and discharging. Okay, and in this case, the two tanks are pressurized alternatively with the compressor of the gas turbine. Okay. In the next slide, you can see the details of the system, the atmospheric valves, the solar receiver, the regenerative system. So the whole system is here, and the actual aspect of the system once it's installed in Almeria. Okay. Well, what are the main results? We have a successfully tested in Almeria, the heliostat, the solar receiver, and the regenerative system with a 300 kilowatt thermal prototype at Plataforma Solar de Almeria. The combined cycle have, as you know, a better solar to electric efficiency than any other system. We have for a concentration of 500. We can change these numbers depending on our assumption. So this technology have a great potential. And in addition to this, we are thinking in other applications of this concept. One is to couple this concept of capture to compress air energy store. This could be very useful for the clean energy transition by charging the compressed air energy store when there is excess of energy in the grid, and then by driving together this system with the CSP and the storage, we think that this could have advantages for the energy storage in the grid. Okay. Other application for the future is to use thermochemical reactions. Okay, in other systems you need to have the thermochemical reaction in the receiver, and as you know, handling a thermochemical reaction with solar is difficult because you need to keep the steady state as much as possible. So by moving the thermochemical reaction from the receiver to the regenerator system, we can have a better control of this reaction, and then we can have a benefit of this. And finally, also this system, or this idea, can be coupled to the desalination system. Today, if you couple to a desalination system with a Rankine cycle, the overall efficiency of the whole system is lower because the steam cycle has penalties once it's coupled to the desalination system. If we do this with a Brighton cycle, we are going to avoid the penalties in the cycle. On the other hand, we are going to have high temperature that is able to run the multi-effect distillation system at higher temperature and therefore at higher efficiency. And also we are going to reduce the water consumption. So these are other applications of this concept. And then other recent development that we are doing here at CENER regarding solar towers, or trying to pave the way for the solar towers. One is the ATMOS system. It's a system to measure the atmospheric attenuation in real time. And with this system, we try to measure, here you can see a clear day and the same landscape with a hazy day. So what we want to measure is the amount of energy that is absorbed by the atmosphere when it's reflected from the heliostat to the tower. Okay. In our system that is nowadays installed in a solar power, but we have a white screen here. Okay. We have a reference system in the land that is the white screen here. Okay, the reference system. And we have the measurement system that now is, in this case, is installed on the top of the tower. Okay, this is the top of the tower. So what we do is the white screen is illuminated by the sun. So then this system is a telescope that is able to measure the whole spectra of the whole solar spectra. Okay, and then once we measure this spectra, then we take the second spectra from the tower, and by comparison we can measure the atmospheric attenuation at any wavelength. But give us not only the information about what is the effect of this atmospheric attenuation with a high accuracy, but also let us know what is causing this atmospheric attenuation and in which wavelength. Okay. The final accuracy of this system is around 0.5% for relative attenuation measurement and about 1% for absolute attenuation measurement, and these are the main features of the systems. Okay. In addition to this system, we are also developing an advanced heliostat characterization system. In the state of the art, what we do to characterize a heliostat is we use the reflected image of a heliostat in a white target. With a camera, we take a picture of these flags reflected on the target, and with this information, we try to make the evaluation of the beam quality and also the quality of the heliostat. Of course, these have some difficulties. Okay. Then one of the limitations is, of course, the target site. Sometimes, especially for the heliostat that are placed at long distance, the affected image of the sun do not fit in the target. Okay, do not fit in the target. So this is a problem. The other thing is the target quality. Not always the target is Lambertian. Sometimes it's dirty. Also, the problem is the camera sensitivity. The signal to noise ratio is not good enough. Other times, the heliostat from the last rows, the density on the target is also very low. So it's very difficult to measure this with a high degree of quality. In our system, we are removing the white target and also the camera, and we are placing a pole. In this pole, we place an optoelectronic device, and this device are the following. We have the detectors. These detectors have some lenses to increase the signal to noise ratio, and also they have a variable gain amplification system, but allow us to have always a very good signal to noise ratio under any circumstance. We have also pinhole cameras. With these pinhole cameras, we are able to know where the energy is coming from in the heliostat. We can make a very easy ray tracing. So we are going to know much with more detail the information from the reflected image of the sun. The pole is fixed, and this pole scan the reflected image of the sun from the heliostat. The heliostat is also fixed. And by scanning this image, we can reproduce the reflected image of the sun, and also to get with very high accuracy all the measurements. Other advantage of this system can be easily installed during commissioning to test the quality of the heliostat, and also during operation. We can place this pole on the top of the tower, even at different heights, so we can run in parallel different systems, and we can check the optical quality of the heliostat not only at the beginning of the commissioning, but also during the whole life of the plant. So these are the main developments that we are doing related to solar towers. So the conclusion is, according to all the studies, but also according to my own perception, is that the solar power tower has still a great potential of reduction, but we are facing some problems, as you are fully aware. So in this project, we, with our partners, we are fully committed to pave the way of this technology to overcome the technological barriers. Okay. Thank you very much for your attention. Do you have any questions?